Hello friends, warm welcome in this video, that is the substrate inhibition. Friends, what is the meaning of substrate inhibition? Substrate inhibition is the type of inhibition in which enzyme is inhibited by the substrate itself at a high substrate concentration. You can see in this picture that the enzyme possesses two sites. One is active site and another is a regulatory site. If the substrate binds to the active site, then it will convert into the product. But at high concentration, if the substrate binds at the regulatory site, then the substrate may inhibit the enzymatic reaction. So it seems that it is very similar to the uncompetitive inhibition. Yes, it is very similar to the uncompetitive inhibition. Only the difference in the uncompetitive inhibition and substrate inhibition is that in the uncompetitive inhibition, the inhibitor is other than the substrate, whereas in the substrate inhibition, the inhibitor is itself substrate. So see this reaction diagram. In this case, E plus S will give ES complex, which again converts into enzyme plus product. Now to the ES complex, a second substrate may bind and it will convert into SES complex. Now this SES complex may again dissociate into ES complex, or as the substrate leaves, it may convert into product. So as it is very similar to the uncompetitive inhibition, we know the kinetics for the uncompetitive inhibition, the equation for the reaction rate of the uncompetitive inhibition, that is V0 is equal to Vmax into S0 divided by 1 plus concentration of I0 divided by Ki whole divided by concentration of S0 plus Km divided by 1 plus I0 by Ki. But as we know, here the inhibitor is itself substrate, and therefore we will write instead of I0 S0. So the equation will become V0 is equal to Vmax into S0 divided by 1 plus S0 divided by Ki whole divided by concentration of S0 plus Km divided by 1 plus concentration of S0 divided by Ki. Now if we multiply this equation at denominator and numerator with 1 plus S0 divided by Ki, then we will get V0 is equal to Vmax in bracket concentration of S0 divided by concentration of S0 into 1 plus concentration of S0 divided by Ki plus Km. So this is the very similar equation to the Michaelis-Menten equation. But when concentration of S0 is very high, then concentration of S0 in bracket 1 plus concentration of S0 divided by Ki bracket close plus Km is approximately equal to concentration of S0 in bracket 1 plus concentration of S0 divided by Ki, because here the affinity of the substrate to the enzyme is very low or negligible, and that's why Km is negligible and we have not written here Km. So under these circumstances, the reaction rate will be V0 is equal to Vmax divided by 1 plus concentration of S0 divided by Ki. So here if we plot the Michaelis-Menten curve under the presence of high substrate concentration, then we will get curve like this. In this case, the velocity rises to a maximum and then descends. So this is the Lineweaver plot which can be obtained from the equation. Surprisingly, in about 20% of the enzymes, the phenomena of substrate inhibition occurs. Substrate inhibition is often interpreted as an abnormality that comes from using artificial high substrate concentration in the laboratory setting. Probably the main reason for this neglect is that the majority of enzymologists and many authorities in the field regard substrate inhibition as being almost always non-physiological phenomenon. But there are several reasons for suspecting that substrate inhibition is not a pathophysiological phenomenon but a biologically relevant regulatory mechanism. The reasons are: first, in many cases, normal substrate concentrations are to the right of the velocity maximum, which indicates that these enzymes typically operate under substrate inhibition. Second, many enzymes have specialized sites where a second substrate molecules can bind and acts as an allosteric inhibitor. For those enzymes, substrate inhibition is clearly a specialized evil property. The third evidence is accumulating that substrate inhibition plays critical regulatory roles in a number of metabolic pathways. This is the list of some common enzymes showing the substrate inhibition. Tyrosine hydroxylase is the enzyme which catalyzes the conversion of tyrosine to L-dopamine. This enzyme shows strong substrate inhibition by tyrosine. The second example is phosphofructokinase, which converts fructose 6-phosphate to fructose 1,6-bisphosphate. This enzyme is also inhibited by the substrate fructose 6-phosphate. The third common example is pyruvate kinase, which converts phosphoenol pyruvate to pyruvate and inhibited by substrate phosphoenol pyruvate. Urease is also an important enzyme which is inhibited by substrate urea, and the succinate dehydrogenase is inhibited by succinate. Succinate dehydrogenase is responsible for converting succinate to fumarate, the intermediate of Krebs cycle. So now we will see the example of succinate dehydrogenase in detail. So let us consider the possible mechanism for substrate inhibition at a high substrate concentration in relation to the reaction catalyzed by succinate dehydrogenase. Here, for reaction to take place, both carboxyl groups of the substrate have to bind the enzyme like this. But at a very high substrate concentration, there is an increased possibility of a carboxyl groups from two separate substrate molecules binding to the same enzyme like this. So if this happens, the reaction cannot take place until one of them has dissociated away. So this example clearly illustrates that how substrate inhibitor inhibit the reaction mechanism. Thank you.